Hello everyone, my name is David Jones and I'm a Senior Nanofabrication Engineer at the Quattro Nanofabrication Facility at the University of Pennsylvania. This video series will teach you how to draft designs for micro and nanolithography using LayoutEditor. Before you take this training, we suggest the following. Set aside 2 to 3 hours in your schedule to go through the training. That should give you enough time to work through the lessons. Use a mouse instead of your laptop's touchpad. Most people tend to find using a touchpad with LayoutEditor to be a bit tedious and cumbersome. Of course, download and install LayoutEditor. You can type in the link from this slide, or you can simply Google LayoutEditor download and download it from their website. You can use LayoutEditor for free, but the full version requires a license. Users of the Quattro NanoFab can use the QNF site license. To get a copy of it, please send an email to qnf-process@lists.cs.upenn.edu asking for a copy. Also, please don't be afraid to ask the staff for help on your design. We're always happy to help answer any questions, provide guidance, etc. First, we'd like to give you an idea of what you can do in QNF lithography. The lithography tools in the QNF can handle a variety of substrate sizes. We can handle any size substrate up to 6-inch wafers, which includes 4-inch wafers in pieces. If you'd like to pattern your features down to about a micron in minimum feature size, you should consider using the SUSE MA6 mask aligner. The exposures on this tool are usually pretty fast in that they only take a few seconds, but they're limited in minimum feature size versus some of the other tools that we have. If you'd like to make photomasks to use in the mask aligner or print features down to around 400 nanometers in minimum feature size, you should consider using the Heidelberg DWL66 Plus laser writer. This tool writes on samples directly, so exposures take longer than they do on the mask aligner, but it's capable of printing smaller features than the mask aligner can. And if you need to print features smaller than 400 nanometers, you should consider using the Alionics ELS7500EX electron beam writer. This tool can write features down to somewhere around 20 nanometers, but the write times for the Alionics are much longer than they are for the Heidelberg or the MA6. Now you might ask, why should we use LayoutEditor? Why can't I just use AutoCAD, SolidWorks, or one of those other programs? Now that's a good question, so let's answer that now. LayoutEditor supports a format known as GDS, or Graphic Database System, which is industry standard for lithography. AutoCAD, SolidWorks, and the others do not support this format. But they do support a format called DXF, which may be used for lithography. You should be warned, though, that the DXF format is prone to certain problems that the GDS is not. So let's illustrate the top issue that folks encounter with the DXF format with an example. Suppose I draft my design, 2 boxes in a rectangle, in the GDS format. When I go to convert that design to the language that the write tool understands, or the data preparation as we call it, everything converts just fine. Now let's suppose I draft that same design in AutoCAD, 2 boxes in a rectangle, just like what I did in LayoutEditor. I go to do the data prep, and wait a minute, what happened here? The rectangle didn't convert. This is because the rectangle in the middle was actually drawn in 2 separate line segments, but to us it looks like a rectangle. The result is that the middle rectangle is not a closed object and thus does not convert. And so when you go to do the lithography, that shape goes missing. It's common for shapes drawn in DXF format to go missing in the final print for this reason. Now before we jump in and start using LayoutEditor, there are a couple of foundational concepts that we should lay the groundwork for. The first is this concept of hierarchy. So, anytime we draw anything in LayoutEditor, we always do so in a cell. You can see here that I've drawn a box and 2 circles in this cell, which I'll call cell 1. From there, I can create a new cell and create references to the first cell. I'll call this one cell 2. These look like unique objects, but they're not. They're actually just references to cell 1 in this case. Now let's suppose I make a change in cell 1. When I do that, the change will get picked up everywhere else I've dropped in one of these references to cell 1. In this case, I dropped in references to cell 1 randomly, but we could also array them instead. I can specify the number of units in X, the number of units in Y, the pitch in X, the pitch in Y, and so on. Now in practice, we use this concept to build everything from very simple designs, like this line space array, to very complex designs like this MEMS device here. So let's take a look at this complex design. This cell that you see here is what we call the top cell, or the merge cell of the design. This contains the final design that we'd like to print onto the mask or the sample. In this case, this cell is made up of a few cells: O3 chip, O4 chip, O5 chip, and some alignment marks at the edges, and so on. Let's take a look at this middle cell called O4 chip. And now this cell is comprised of a few other cells: a contact pad array, a couple of comb drives, and so on. And this comb drive cell here is made up of other cells: comb 24 gap, mobile electrode, bar 36, and so on. And at this point, you can see this sort of hierarchical tree developing. Now here's the key. If we make a change to one of these cells at the base of the hierarchy, that change will be picked up everywhere else in the design that it's referenced. If we'd like to change the design later, that'll be much easier to do if we drafted our design using hierarchy instead of just putting everything into one cell. The next concept is this concept of a layer. To understand layers, let's look at a real example. This is a device made at the QNF using the design from the previous slide. First, this white-looking material is some metal, and this purplish-looking material is device silicon. In the design, that corresponds to these two layers. The process was designed so that layer 2 from the CAD ended up as metal on the wafer, and layer 1 from the CAD ended up as device silicon. Now some folks might ask, do you have to design the metal into layer 2 and the device silicon into layer 1? What if you wanted to change the two? And the answer to that is, it doesn't matter which layer you design which material into. You could design the metal into, say, layer 12 or layer 42 if you like.